Welcome to This Explainer. Today, we're going to unravel an invisible string. It's a single, elegant principle of wave mechanics that literally governs the reality around us. And I mean everywhere, from the microscopic blood cells flowing through your veins right now, all the way out to the unimaginable scale of distant galaxies rushing away from us in the dark. So, what exactly connects a beating heart to the edge of the expanding universe? Sounds kind of poetic, doesn't it? But the answer isn't philosophy at all. It's pure, measurable physics. It's a phenomenon you've personally experienced every single time an ambulance drives past you with its sirens blaring. Yet, this exact same principle holds the key to modern medicine, severe weather prediction, and our fundamental understanding of the cosmos.
I'm talking, of course, about the Doppler effect. You probably know the standard textbook definition: a shift in the frequency of a wave relative to an observer moving compared to the source. This is our invisible string. Whether we're looking at sound waves in the air, ultrasonic waves deep inside human tissue, or electromagnetic waves stretching across the sheer vacuum of space, the rules remain exactly the same. And by mastering this shift, scientists and engineers have unlocked the ability to measure the velocity of practically anything in existence. Our roadmap for today is pretty straightforward. First, we're decoding the Doppler effect. Then we'll look at the mechanics of radar, tracking storms and skies, radar in modern medicine, and finally, industry and the cosmos. Let's jump in. Section 1. Decoding the Doppler effect, the physics of stretching and compressing waves. All right, before we get to the complex machinery, we've got to visualize what happens to a wave when it interacts with a moving target. It's a clinical absolute rule. If an object is moving closer to the source, it compresses the waves in front of it. The distance between those waves actually shortens, which creates a higher frequency. In the light spectrum, we call this a blue shift. Conversely, if the object is moving away, the waves stretch out behind it. The wavelength gets longer, resulting in a lower frequency, a red shift. If you can measure that exact shift, you know exactly how fast that object is moving. It's brilliant. Moving right along to Section 2, the mechanics of radar, capturing the invisible shift. So, human ingenuity basically took this simple physical truth and built extraordinary sensory organs to capture it. Take a basic continuous wave, or CW radar. It's super simple. It constantly transmits a stable frequency, which makes it fantastic at detecting velocity. Think of a police speed gun. But the catch is, it's entirely blind to distance. To fix that, engineers came up with frequency-modulated CW radar. By sweeping the frequency, it reveals both distance and speed, which is great for tools like aircraft altimeters. But the heavy lifter, the most advanced system that really runs our modern world, is pulsed Doppler radar. It gives us both range and velocity through some incredibly sophisticated timing. Now, pulse Doppler is doing this really delicate balancing act. Instead of a continuous beam, it fires off a brief, super powerful pulse of energy. Then it immediately goes completely silent just to listen. By measuring the exact time delay before the echo returns, it calculates the range. Pretty standard. But to get the speed, it looks at the phase shift between successive pulses. If an object is moving, the returning wave's phase shifts just a tiny bit from one pulse to the next. That microscopic delay across pulses is the Doppler shift. But here's the catch, and it's a big one. This elegant solution creates a massive engineering headache known as the Doppler dilemma. If you want to measure something moving incredibly fast, you have to send your pulses very, very close together, a high pulse repetition frequency. This raises what we call the Nyquist limit, allowing you to see high speeds without the data literally folding back on itself, which is an error called aliasing. But wait, if you fire pulses too quickly, you don't leave enough silent time for echoes from distant objects to return. The radar gets totally confused about which pulse an echo actually belongs to. So you can have accurate high speeds or accurate long distances, but you always have to trade one for the other. Section 3. Tracking storms in skies, atmospheric applications. When we bounce these radar pulses off tiny targets floating miles above our heads, we can actually map the invisible currents of our atmosphere. Think about it. When a radar pulse hits a raindrop, the Doppler shift tells us the exact wind speed. Meteorologists are constantly scanning for intense, high-speed rotation, like a hook echo, because that is a massive red flag for tornadoes. And because Doppler detects speed, modern digital processors use what's called a notch filter to completely delete stationary ground clutter. It just wipes the mountains and buildings from the screen, leaving only the moving storm cells. For aviation, this is how we detect invisible, sudden downdrafts and wind shears. It's a technology that literally saves countless lives every year. Section 4. Radar in modern medicine, from ultrasound to contactless care. You know, the Doppler effect isn't just for scanning the massive expanse of the sky, It is tied directly to the human cardiovascular system, 1,540 meters per second. That is a vital number in clinical cardiology. It's the accepted constant speed of sound traveling through human tissue. When a cardiologist does a Doppler echocardiogram, those sound waves bounce off your moving red blood cells. The machine then uses this constant to calculate the exact velocity of your blood flow, right there in real time. But to handle the crazy range of velocities inside your heart, doctors rely on the exact same radar concepts we were just talking about. They use pulse wave Doppler to look at a specific, precise depth, say, exactly to valve. But remember the Doppler dilemma? If your blood is pumping too fast, the signal aliases. So, to measure the extreme velocity of, say, a severely narrowed stenotic valve, they switch over to continuous wave Doppler. They sacrifice depth accuracy, sure, but they capture the highest speeds flawlessly. The machine then color codes this data using the BART convention, blue away, red towards. And by taking that peak velocity and plugging it into the simplified Bernoulli equation, doctors can calculate the precise pressure gradient inside your heart entirely non-invasively. It's absolutely brilliant.
And medicine is moving way beyond traditional ultrasound. Today, actual electromagnetic radar is being used for contactless health monitoring. Get this, by emitting super low power 24 or 60 gigahertz millimeter waves toward a sleeping patient, the radar detects microscopic phase shifts. What's causing the shifts? Just the mechanical vibration of a heartbeat and the gentle rising of a chest. Without a single wire attached to the body, Doppler radar can accurately monitor heart rate variability and even diagnose obstructive sleep apnea, right through blankets and clothing. Finally, Section 5, Industry and the Cosmos, Scaling to the Extremes. From the quiet intimacy of a sleeping patient, the true universality of the Doppler shift becomes pretty awe-inspiring when we push it to the extremes. Take this massive frequency, 340 gigahertz. Researchers recently developed a terahertz radar system operating at this sub-millimeter band to look inside fluidized bed reactors. Now, these reactors are chaotic, totally opaque environments used to convert solid biomass into green energy. Before this, seeing what was happening inside was practically impossible. But using pulse Doppler radar at 340 gigahertz, they achieved unrivaled precision. They can now measure the flow of solid particles in real time, optimizing fossil-free fuel production like never before. And when we tilt our sensors away from Earth entirely, the Doppler effect proves to be our most powerful tool for exploring the universe. When a distant star has an unseen planet orbiting it, the planet's gravity pulls just slightly on the star. This creates a tiny rhythmic wobble. As the star wobbles toward Earth, its light waves compress into a blue shift. As it wobbles away, the light stretches into a red shift. By measuring this microscopic Doppler shift, astronomers have successfully discovered entirely new, invisible worlds orbiting distant suns. But I think the most profound realization comes when we look at the galaxies themselves. The red shift observed in distant galaxies directly supports the Big Bang theory, indicating that the universe itself is continuously expanding. The light from nearly every galaxy we observe is stretched. It's shifted toward the red end of the spectrum. And the further away they are, the more stretched the light is. Think about that. The exact same mathematical principle that catches a speeding car on the highway and measures the blood rushing through your heart is the definitive proof that the fabric of reality itself is expanding. So let's end on this thought. If a single principle of wave physics can both measure a beating heart and unravel the very edge of the universe, what other invisible strings are hiding in the frequencies around us? The Doppler effect is this beautiful reminder that no matter the scale, whether it's microscopic or cosmic, the universe speaks in a singular mathematical language. It's really just a matter of us learning how to listen to the echoes. Thank you so much for joining me on this deep dive. Stay curious, keep exploring, and I'll catch you in the next explainer.